Okay, here are some fundamental laws which will help us to analyze logic gates and when they're connected together. Of this fundamental laws. So these are related to the OR gate. If you have A, which is an input, and you have 0, which is the second input, then that result will always be A, which is kind of obvious, right? But 0 won't really change anything. However, if you take A, which is one input, and 1, then the output is always 1 because you're ORing 1 with A, which is a binary, 0 or 1, no matter what A is, the output will be 1. Here, A is an input. We have A plus A equals A. And if you have A plus the complement of A, so if A is 1, then A complement would be 0, and that will always be equal to 1, no matter what the input is. Similarly, we can do things with and these are just useful when later on when we try to simplify complicated logic expressions. So A dot 0, so A and 0. Anything which you dot with 0 is going to be 0. A dot 1 is A dot A. So that the two inputs, if they are A, then that is going to be just A. So 1 times 1 is 1, 0 times 0 is 0. That's what it's saying. If you take A times A complement, remember that one of them will be 0, which means that this expression will always yield 0. And then finally, not. The only thing I want to say is that if you take if you invert an input and you invert it a second time, so that it's like you connect you have a NOT gate and then you have another NOT gate, then this is going to simply come back to you as A, because you're inverting it twice. 2 negatives make a positive. So similarly, 2 NOTs will make the original signal. Okay, so that's some of the properties. Here are more. Second, commutative laws. So if you have A and B, so the inputs to the OR gate are A and B, and then you swap the inputs to B and A, then it turns out that the output would be the same. It doesn't really matter. If you have an AND gate, and if you take 2 inputs, A and B, and then you change them, swap them out as A and B swap, then B times A will be the same as A times B. So A and B is same as B and A. Then we have the associative law. Here we have, let's say, A plus B. So that's an OR gate. And then we connect the output of A plus B to another OR gate. Then it turns out that you could also pass B and C through an OR gate and then take the other OR gate through A and output of B and C. And that will basically work out to be the same. So that's kind of, it seems very obvious, but it's important to note that that's true for logic gates when you're dealing with zeros and ones. Similarly, if you have AND gate and then you multiply it with C, so first you AND and then you have another AND gate, and that's the same as taking B dot C and then doing the AND. In fact, you can also actually swap A dot B same as B dot A, which I wrote down here. And so this could also be written as B dot C dot A, and the place where this comes from is from here. Okay. Then, so that's not associative, but it is basically from the commutative law. Okay, the fourth one is distributive law is actually laws, distributive laws. So here we have, let's say, we take the AND of A and B or C. So B plus C means is an OR gate, and then you connect that to A through an AND gate, then this is the same as A dot B plus A dot C. You can recognize this very similar to how we would write any mathematical expression. A times B plus C will be the what I've written on the right side. Similarly, if you have, this is probably not non-intuitive. If you have A plus B dot C, turns out that this is the same as A plus B dot A plus C. Now, this is less intuitive. Right? How is that true? That's probably not true. If you take any numbers in decimal system, A and B and C, and then that's probably not going to work out as it is. But we can actually prove that. Here. So what we can do is two ways to prove it. One is you can try to simplify that expression and show that it's true. But remember that A, B, and C are binary inputs, zeros and ones. So in order to prove something, you need to exhaust all the cases. So you can just draw a truth table, take all the inputs, A, B, and C if the left-hand side works out to be right table. So let's check this, just to give you a height of this. Prove this. So one is simplify. The second way to prove this is truth table. Okay, let's use the latter. And then I'll show you some examples where we'll prove it without using the truth table. So what we have is we need to prove that A plus B dot C equals A plus B dot A plus C. Okay, so here we go. We have three inputs, A, B, and C. We'll try to create all the possible combinations of A, B, and C. So what we do is we start with, let's say, 0, 0, 0. Okay, now we can start increasing the bits one at a time. So those are all the combinations of B and C, but that will go with 0, 0, 0. Now I've exhausted all the BC with A, but now I'm not considered when A is 1. So let's do that. 1, 1, 1, 1. And so all combinations would be 0, 1, 1, 0, 1. Okay, so what we're trying to do here is we're trying to get the expression A B dot C. So let's just compute B dot C. Okay, now you could do this in your head. That is, you can figure out what A plus B dot C is in your head and write it down. But I think it's just easier if you just go one step at a time. So B dot C, we just take the product of these two. That's about it. Then we can compute A plus B dot C. Okay, so all we do is add A to this column. So 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 0, 1, 1, 1. Okay, so that basically gives us one of the expressions. Let's get the other one. Easier to do A plus B first, and then A plus C, and then we'll do the multiplication. So A plus B is A plus B, 0, 0, 1, 1, 1, 1, 1, and 1. Let's do A plus C. So 0 plus 0 is 0, 0 plus 1 is 1, and so on. 0, 1, 1, 1, 1, 1. Okay, and then finally, we get to do the dot product. So A plus C dot A plus B dot A plus C. Okay, so we just need to multiply these two together. 0, 0, 0, 1, 1, 1, 1, 1. And so the final step is, in order to verify this expression, all we need to do is compare these two columns. Okay, so you can see that they actually check out and so on, which means that we've verified the expression. So now when we normally do something, we prove things in the world of mathematics, we usually don't do something like this. We just don't do enumeration like we've done here. But because this is sort of, there are only 8 combinations, we can actually brute force prove that it's true by considering all cases. Now, if that was not true, that there were more values for A, B, and C, would not be possible to check it this way. Okay, so here are some other identities, and we'll be using this later on. We put them down. Other useful identities. Okay, A plus A plus A dot B is just A. A dot A plus B is also A. A plus A complement times B is A plus B. A plus B and with A plus B complement is going to be A dot B plus B dot C plus B complement dot C equals A dot B plus C. And then A dot B plus A dot C plus B complement dot C equals A dot plus. Okay, you can verify all of these using either simplification or truth table. Let me just show you how to do this by using the formula. So prove these either using simplification or truth table. Okay, let me show you how to do this now without using the truth table. Okay, example. Okay, we'll prove, let's say A plus A dot B equals A. Okay, how do you prove something like this? Okay, so let's start with the left side, A plus A dot B. You could write this as 1 dot A plus, let me write it as A dot 1 plus A dot B. Now, why did I write that? Well, we've seen that one of the rules here was that with the AND gate is that A dot 1 is A. Like I'm going to use a similar one, but it's also obvious that A dot 1 is going to be A. We don't really need to turn back pages and see it, right? So we write it this way. We can then simplify this. Well, we can use the distributive property, which is I can pluck the A out as common. That is A dot 1 plus B or 1 plus B, right? But 1 plus B is 1 because anything with 1 is going to be, any OR with 1 is going to be 1. So this is A, which is the right side. Okay, this sort of proves without using the truth table that that's true. So that was very simple. Let's take a more slightly more complicated expression and try to see if we can play with it. I'm going to show, well, example. Okay, so let's see if we can prove that another expression wrote was A plus, so sorry, prove this A plus B dotted with A plus B complement equals A. Okay, clearly you don't want to start with the right side because it's much harder to do it, but probably better off to start with the left side. So we have on the left side A plus B dotted with A plus B hat. Okay, so now we somehow need to get rid of the brackets and we can turn back and see what expression holds true. So we had A plus, let's see, A plus B dot. So we're trying to see if we can, maybe this one will work, right? If you have A dot B plus C, the same as A dot B plus A dot B. So what you can do is you can think of this as, I don't know, C. So then C dot A plus B is the same as C dot A plus C dot B complement, but C is nothing but A plus B dotted with A plus A plus B dotted with B complement. Okay, now the same property. So let me just write down what this was. This was basically using the fact that A plus B or C, A plus B dot C, the same as A dot C plus B dot C. Again, clearly this is, it's probably written slightly differently here. Let me check. It's A, okay, it's written the same way, but what I was going to say is if it was swapped, you can always swap it because A dot B plus C is same as B plus C dot A. Right? That's also true. So let's go back to this. I use this property, but I can use this property all over again. So it's same. I can use the same property next step. So I can distribute this A with this 2. So A dot A plus B dot A plus A dot B complement plus B dot B complement. Okay, so the same thing will come from the same, we use the same property. Now let's say how we can simplify this. We have A dot A, we know that A dot A is A, right? 0 times 0 is 0, 1 times 1 is 1, which means that A times A is just A. Here, what we can do is, in order to simplify this, maybe it's best to pull out A. So I'm going to write this as A dot B plus A dot B complement. Note that I switch the order of A and B because they're commutative. And then B dot B complement has to be 0 because 0, if you take 0, B is 0, then 0 times anything is going to be 0. But if you take B equals 1, then B complement will be 0. So that should be 0. Okay, so let's now pull this A out. We have B plus B complement, but B plus B complement is always 1, which means that this is A, which is the right-hand side. And which proves that it is A. And so this is the answer. So this is the other way to prove expressions are true. Okay, the last one, and then we'll go to other things. So sixth one, and this is probably very important when we synthesize circuits. It's called a De Morgan's law. Again, we'll be using it quite a bit. So we have A plus B plus C plus so on equals kind of non-intuitive. It is A dot A complement dot B complement dot C complement and so on. Okay, and similarly, if you have A dot B dot C dot so on, okay, so the whole complement is A complement plus B complement plus C complement plus so on. Okay, note that this is different from this expression. The difference being that in the top one, you have the complement of individual inputs, A, B, C, but down below, you have the complement of the product. The complement of the product is different from the product of the complement. Okay, and why this is important is because it can convert or rather NOR to AND or NAND. So this is the plus means it's OR, the complement means it's NOR. You can convert that to a dot product AND. Okay, and we'll see a little bit later on that this is very useful if you want to minimize the number of logic gates you might need in order to build a circuit. Okay, the question is simplify the Boolean expression to minimize the number of logical expressions. Okay, I'll tell you what I mean by that. So let's say that your output Y is C plus A dot B plus A dot C plus B dot A complement. So you have three inputs, A, B, and C. And then let's say that this models something you're trying to do, like, I don't know, some logic is modeled by this expression. And we'll get to this point of this question of how do you design a logic gate based on some conditions given to you. That'll come next. But here, let's focus on simplifying this expression. Let's say you're told to build this out of logic gates. So then you ask, how can I build this? Okay, so first we'll look at the number of logical operations involved. We see that there is 3 pluses, right? Which means that you need 3 OR gates. We see that there are this one, this one. Okay, then we see that there are 3 AND operations, right? Which means that you need 3 AND gates. And then we notice finally that there is 1 NOT gate. Okay, so to we have this particular 7408 is an AND gate, and instead of 4 gates on one chip, which means you need just one chip because you can use three of those AND gates on that chip. Right? We need 3 OR gates. So we have 4 on 7432. So we need 1 7432, and then we need one NOT gate, which is 7404. So we can use that. So we need 1 7408, 1 7432, and 1 7404. We can write here 17432, 17408, and 7404, I think. 1, 1, 1. So 3 ICs, 3 gates, or 3 chips. Okay. So now let's see if we can simplify this in order to reduce this number of expressions, which will reduce the number of chips we need to use. Okay, so let's take this. Okay. And let's see if we can perhaps combine the middle two. So I use the associative property, B plus C plus A complement. Okay, now I think I've seen this A dot B plus C. I can go back to here maybe. Maybe not. Let's see. A dot B plus C. Not here. Yeah, here it is. A plus A dot B plus C. A dot, no, I thought it was this. It's not that. So maybe I can't do that. Let me just try to change my mind, not combine those, but maybe we can combine this one and this one. It might be better. So C plus, I just write this down here. A dot C, it's no problem if I switch. And I can write this as B dot A plus A complement. Okay. So C plus A dot C plus B dot, so A plus A complement is 1. Okay, so that simplifies it. Here, maybe I can do something like this. 1 dot C plus A dot C plus B. This is 1 plus A dot with C plus B. And then you see that this is nothing but A plus 1 is 1. That's B plus C. So we've reduced an expression which required 3 OR, 3 AND, and 1 NOT to just 1 OR gate. 1 OR gate, which means that if you look at this, all you need to do is you need 1 7432. Use 1 7432. That's it. So simplifying makes your life easy, less wiring.